This is a differential equation for some unknown function x of t, right? So what that means is that what this being a differential equation means is that for some unknown function x of t, this equation over here contains the derivatives of this unknown function. This equation is for this unknown function, and it contains the derivative of this unknown function. And so that may be hard to grasp at first, but let's look at it like this. If we set, now by the way, this equation is probably going to be familiar to you because remember Newton's second law. So Newton's second law, what does it say? It says F is equal to ma, right? Which means that which roughly means that the acceleration is equal to the force divided by the mass. Now it's similar over here. You can see that some constant force divided by the mass is equal to the acceleration over here. And now that may be a little confusing. Maybe like, okay, why didn't you just write it as a? And the reason is, if you write it like this, it's more effective, and you understand that there's more going on in the equation, and that this is a much more complex equation than what it seems to be at first sight, right? So let me explain that. So let's denote x. If x is equal to position, then the derivative of position is equal to velocity. The derivative of velocity is equal to what? It's equal to acceleration. And a good way to denote that would be to write x, so the x with two dots denoting second derivative. This would also mean that the x is the first derivative of velocity. That's why we write one dot for first derivative, two dots for second derivative, right? This way we understand better. And now this would be x with one dot, the first derivative of velocity of position. Now, another thing that the acceleration is it's the derivative of velocity, which we know with respect to time. So that's important. This is a function of time. And that's how we could solve this. What we're trying to do is we're trying to get back to the original unknown function. What is the unknown function that this is a differential equation of? Right? That is the question. So to do this, since we know we're at the acceleration, a good way to get back to the position function, which is over here, is to just simply just say, we'll just integrate this twice. If we do that, then in that manner, it'll be much easier than if we rush into it doing anything else. So let's replace this with dv over dt. So dv dt is equal to the constant force divided by the mass. Now let's multiply both sides by dt. Now this cancels out. We're left with dv is equal to force, the constant force, divided by the mass times with respect to time. Now let's take the integral, because this is a derivative. The derivative will cancel, right? So let's just write it like this. dv from the initial velocity, some initial velocity, to some velocity time t. So we're trying to find out the velocity at any time t, the total velocity. We want to know what it is, right? We could just set this equal to the integral of this side. This would be from time with respect to time, so 0 to any time t, any constant force divided by mass with respect to time, the integral of this. Now on the left side, the integral is just the final answer, the final value would just be v, because we removed the d. Now v, we would evaluate from v equals 0, so v sub 0, to v sub t. So from the initial velocity to some velocity at any given time, right? That's the total velocity. It encompasses everything. Now, over here, what we can do over here is we can move the f and m to the front to make things easier. So fm, let me make this better. Whoops. Let me just, oh my god, last try. You know what? Leave it. Oh, I'm going to do it one more time. There we go. Okay. To evaluate this from 0 to t, we'll be left with 1 over here because we've moved this to the front. And remember this, that if we're taking the integral of any constant, let's say the constant is, let's say it's c, with respect to time, the answer will just be the constant times the time. So this will just be equal to ct. And we apply the same logic here. This will just be equal to t because remember, that's the constant law. Over here, let's substitute this. So vt minus v sub 0 is equal to f of m t evaluated from 0 to t, because we still have to evaluate it. Now let's leave this here for a second. Go down here. Let's just leave the left side for now. Let's just finish this up. So f, whoops, remember? Okay, f over mass. Okay, let me fix this because, okay. Alright, so we're evaluating this, so sub t, we sub t, we just get t, then we sub to 0, you get 0. And now you're left with this. And obviously we know the 0 is going to cancel out. We're going to be left with vt, and remember we're trying to find the total velocity, so we'll move this to the other side. We'll be left with f of m of t plus the initial velocity. And the initial velocity is just this. Now we got the total velocity. So what this means is, and remember up here that we said that a is equal to, remember that if you divide the force by the mass, you're going to be left with the acceleration, and here the force is divided by the mass. So just to clean it out, we could just do this. V of t, and we could just write this as a times t. Let me just fix that real quick. A times t plus the initial velocity. So what this means is, if at time equals 0, the velocity is, let's say, 9 meters per second, right? If this is the velocity, by the way, velocity is a vector, so we should be writing this above everything, but it's not meaningful to the discussion right now, so I'm just trying to solve and get to the bottom of the differential equation. So we're just going to excuse that for now. So the velocity, let's say at time 0, time equals to, or t equals 0, is 9 meters per second. Then when we get to, let's say, sometime equals t, right? So sometime t, the velocity is now equal to, well, could be whatever number you want. So let's say 15 meters per second. Is the total velocity, let me make this a little cleaner, is, now the total velocity for the system is not 15 meters per second. You have to account for the initial velocity. This is the accelerated velocity, right? So if a ball or something has some type of velocity right over here, right, at time equals t, so time equals 0, and it's, let's say it's going at 9 meters per second, and then it gets to about over here, and then it's 15 meters per second. For it to increase in speed, it had to have accelerated. That's what we have, the acceleration here, right? But if you want to get the total velocity of the system, you have to account for the original speed too. So just because the speed goes up in some manner, all the way up to 15 meters per second, that does not mean that the 15 meters per second is the final speed. The final speed is this. It's the initial velocity. So in total, in this case, it would be roughly about 24 meters per second the total velocity. So this function helps us understand that. And right now we got to the velocity function. So we integrated once.